So first one is understanding the key features of C language. The next one is applying suitable control structures and arrays in solving real-time problems. Next one is analyze problem statements to design appropriate solutions. You are going to design by using flowcharts. You are going to draw flowcharts. Then you'll be evaluating various control arrays and modular functions. Modular functions in the sense you are going to have a function defined for a particular part of a problem statement. Means if you want to perform a processing operation, for processing you are going to separately write a function. Now that's why we are going to call it as modular function. Displaying part is separated, processing part is separated, taking the input values is separated. In other terms, you are going to write separate functions for all. Separate function for input, taking input, separate function for processing the data, separate function for printing the output. Now all this process is performed in a modular aspect. So that's why we are going to say you are going to evaluate various control arrays and modular functions. Then finally we are having the last course outcome, that is build and document applications for real-time problems. Finally you are going to develop real-time applications. Building means you are going to write the program, compile it without errors, then execute it, is altogether called as build. So you are going to build and then you are going to document. Document in the sense you are going to write why you are writing that particular line. What is the necessity of that particular line which is written inside the program. Altogether you are going to develop these 5 aspects in you once you complete this particular course called as Introduction to Programming. So we are having this syllabus in our first unit. You can take a snapshot, or also you might have received this particular syllabus in your yesterday's mail. In your official mail you might have received. So in our today's class we are going to concentrate on von Neumann architecture and data representation in computer number system if possible. So first one is von Neumann computer architecture. Then we are having data representation in computer number system. Computer number system means we are having altogether 6 different types of number systems. In that we are going to study the top 4. So what we are having, one is binary number system. Binary number system means zeros and ones. A computer understands only binary numbers. Then we are having decimal number system. Decimal number system is from 0 to 9, which we are going to use in our daily usage. Decimal number system. Then we are having octal number system, 0 to 7. Altogether 8 digits will be there. And apart from that, we are having hexadecimal number system, that is 0 to F. 16, totally 16 different types of digits. 0 to 9, then A to F. Apart from this, we are having many other types like Unicode characters are there, the Roman numbers are there, and many others are there which we are not having in our current syllabus. Next, we are having problem solving techniques. Those are of 2 types. One is writing the algorithms as well as drawing the flowcharts. For both of them, we are having properties, constraint of algorithms, different strategies, implementation of their sequences, and then selection and repetition. All these are performed in algorithm as well as flowchart. We are going to study when this part comes, and we are going to write certain examples too. So for implementing all this, you need to have a desktop system or a laptop system. You cannot do all these tasks on a mobile phone. We are going to ask you to share your screens. Most probably from the next lab onwards, we are going to ask you to share your screens, what exactly you are doing. We are going to see, and we are going to grade you also. So in that aspect, you need to have your own desktop system or a laptop for our IP class explicitly. Now coming to the basic definitions before starting the course. What is a computer? A computer is an electronic device. Specifically, we will be having 2 types of devices. One is electrical device, another one is electronic device. Electrical device in the sense which is powered and which is run using electricity, like a tube light is there, it is an electrical device. A fan is there, it is an electrical device. Once you switch on the fan, switch on the line, the light or fan is going to do its work. Provided it is working correctly. Now, coming to a computer is called as an electronic device. What do you mean by an electronic device? An electronic device is the one which is going to govern by based on the electricity as input and which can be completely controlled by a user. Which can be completely controlled by a user. You can start a computer, you can do a part of processing it, you may print a document, you may play a game, anything you are going to do, you are going to control it. So if that is the case, then it is considered to be a electronic device. That's why we are going to say a computer is a electronic device. What it does, it performs only three things. First one is it accepts data, means it takes input. What is the input? Input is data. Data means what? Data may be simple text. It may be numbers. It may be audio. It may be video. It may be any complex graphics or maybe anything. Everything is considered to be data in a computer. The raw one is considered to be data. Once you process the data, the second part of a computer is to process the data. What do you mean by processing the data? A computer performs either reading the data or storing the data and processing it. Reading the data, storing the data and processing it. What do you mean by processing? Processing in the sense it retrieves the data and no, it controls machinery. What do you mean by controlling the machinery? Using C language, you can even control a satellite. See, this class is completed for section F. Nothing to worry. Many new friends are there. In order to overcome that issue of losing some part of the syllabus, we are going to restart the syllabus again. Don't worry. If it is completed, then again you can hear the class. Nothing to worry. Again, it will be refreshed. Okay. Though the class is completed for section F, we are having some friends from section E and section G. So we cannot omit them directly. For that sake, we are going to revise the concept again. Now, what do you mean by processing of the data? The processing of the data means we are going to perform controlling the machinery. One aspect is controlling the machinery. Controlling the machinery means you are going to write the code which controls the machinery. Machinery means it may be your optical disk drive, or it may be a pen drive controlling device, or it may be a satellite which can be controlled using C programs. Okay, using C programs. Or you are going to perform calculations part. What do you mean by calculations part? You are going to take input, you are going to process the data based on the requirement, you are going to process. That is called as making calculations part. So one part of the computer is taking input as the data, then after that it is being processed. Then after the last one is storing and retrieving the data. You are going to store the data on a hard disk, or you are going to store the data on a pen drive or onto any optical disks, or in any other form, that may be a file, etc. Or you are going to retrieve the data from these means you are saving the file. If you want to read it back, then it is called as retrieving the data. Now, whenever you execute any program, you play any movie, you play any audio file, you play a game, whatever you are going to do, that is called as processing. In order to do the processing work, first of all, the data has to be loaded from secondary storage device onto the RAM. This movement is called as storing as well as retrieving. This part is done by CPU. Okay. So altogether, a computer is a electronic device which accepts data, processes data, like making calculations or controlling machinery, store and retrieve the data. Data may be simple text, numbers, audio, video, complex graphics, or maybe anything. Altogether, we are going to call this as the definition of a computer. Then we are having the definition of a system. A system is a set of interrelated parts that operate together to perform a specific task. Somebody asks, sir, is this only for CSC? Don't ask silly questions. If you are having a doubt in the concept, you ask. What you have to do with, is it a CSC class or EC class? What it means, you got a link, you are joining this class, try to get something out of this class. Don't ask silly questions. A system is a set of interrelated parts that operate together to perform a specific task. Okay, what do you mean by system? You might have seen a music system in your home. What do you mean by a music system? A music system comprises of a amplifier, maybe a mic, maybe some speaker boxes. All together they are connected with wires, and all together it is called as a music system. A music system is a system which has dash, 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 dash parts, and they are interconnected using wires. They are going to perform a task. What is the task? The task is to play the music. Okay. In the same sense, a computer is also called as a system. A computer is also called as a system. A system is a set of interrelated parts. What do you mean by interrelated parts? What exactly a system has? A system has a mouse. A system has a keyboard, a monitor, a CPU, maybe speakers, maybe some other devices. They are interconnected with some wires. And what they does, they perform a single task. What is that? Processing the data as provided by the user. So a system is a set of interrelated parts that operate together to perform a specific task. A system is a set of interrelated parts that operate together to perform a specific task. Let us go to the next slide. The next slide is von Neumann architecture. Now, every computer has a architecture. Every computer has a architecture. What do you mean by an architecture? The methodology of arrangement of components. How you are arranging the components is called as architecture. Now, if you consider the example of a house, whenever you construct the house may have a blueprint where a particular room is there, where a particular wire must go, everything will be there in the blueprint. Now that blueprint is also considered to be house architecture or home architecture or building architecture, which is drawn by an architect, than engineer. Now, in the same sense, our computer also has an architecture. What do you mean by architecture in computer? Arrangement of components. On a motherboard, how the components are arranged. Either where we have to place the RAM, where we have to place the CPU, where we have to place other components. All this is performed by the manufacturer of that particular motherboard. It may be Intel motherboard or it may be any other motherboard. Now, the manufacturer is going to place the architecture of that particular motherboard, where RAM must be, where processor must be, where other components must be, such that the processing can be done efficiently and quickly. Such that the processing can be done efficiently and quickly is called as the computer architecture. What exactly computer architecture has? It has the arrangement of physical devices or components as well as the instruction set. Instruction set. What do you mean by an instruction set? The capabilities of that particular processor is called as instruction set. The capabilities of that particular processor is called as instruction set. What do you mean by capabilities? Suppose you visit a particular doctor, a specialist. Now that specialist is specialist in cardiology, for example. Now can that cardiology person can deal with neuro related issues? No. He or she can only deal with cardiology related issues, heart related issues. In the same manner, we'll be having different types of processors. Those processors will have different types of architectures. Based on the architecture and instruction set, they are capable of doing something specific. For example, if you consider a processor which can do addition, subtraction, multiplication, division, and some other task, then that is the instruction set what it has. Suppose a processor cannot execute a Java program, then that instruction set is not supporting execution of a Java program. Like this, some processors are capable of some part and not in some part. So altogether, every computer will have, every processor will have a architecture, that is instruction set. That instruction set is capable of performing operations. Now, we are having basically two types of architectures that are available as on date. First one is called as von Neumann architecture. This is what we are having in the syllabus. It is also called as the Princeton architecture. It is also called as the Princeton architecture. Apart from this architecture, one more is there called as Harvard architecture. Now, what exactly von Neumann architecture is? Von Neumann architecture is going to share the control signals and data signals in a common memory location. Data signals as well as control signals in the same memory. Whereas hardware architecture will have separate memory for control signals, separate memory for data signals. So these are the basic differences. We are going to study the advantages and disadvantages in our last slide. There you can identify what exactly is von Neumann capable of and what exactly Harvard is capable of. So he is von Neumann, John von Neumann, who introduced the first architecture. Now, his name is John Louis von Neumann, and he introduced the first computer with an architecture in 1945 called as electronic discrete variable automatic computer. Electronic discrete variable automatic computer, EDVAC. How it looked like? It used to look like something like this. In a huge room, we used to have huge equipment interconnected with tons of wires. Okay, so this one was the first computer with an architecture. Actually, the first computer was introduced by Charles Babbage, and the name of that computer was Analytical Engine. The first computer was Analytical Engine, but it doesn't have any architecture, specific architecture. It used to have vacuum tubes in it. Now, the first computer which has the architecture is EDVAC, introduced or published by John Louis van Neumann in 1945. This is also called as a stored program computer. Stored program computer in the sense it is going to store the intermediate results that are evalved while executing a instruction. For example, if you see the calculators, once upon a time we used to have calculators, basic calculators. Now those basic calculators are not going to store any results. You have to type 10 plus 20, it is going to give you the result. Then you have to perform the next task. Once you switch off the calculator and again press AC, the complete data is lost. So such type of computers are not called as stored program computers. So this John Louis van Neumann has introduced the first computer with an architecture called as EDVAC in 1945. It is also called as stored program computer. Now, what exactly it has? It has these components. One is input devices. What do you mean by an input device? An input device is the one which gives input to a computer. Any device that gives input to a computer is called as input device. Now, for example, a computer has input devices through which it takes the input are, one is keyboard. Whenever you press a key on the keyboard, that is passed to the CPU as input. That's why it is called as an input device. Next one is mouse. You are going to use your mouse to move the cursor. Now, that cursor as well as clicking, many things are performed by a mouse. 70% of the input is given to a computer by the mouse. Hence, mouse is also a input device. Mouse is also a input device. Then apart from this, we may be having n number of input devices, like scanner is an input device, maybe a mic is an input device, and many other input devices are exist in the market. You can simply Google them. And go to Google and type different input devices. You'll be getting a list of input devices that are available in the market. So these are some of the input devices. What exactly an input device does? An input device gives input to a computer. Then coming to the output device, vice versa, the output device is going to take the output or the signals from the computer. Some of the examples of output devices are monitor. A monitor displays the output received from a processor. Next one is the printer. Whenever you press Control P on a particular document, if a printer is connected to it, it is going to print that particular document. Now that printer is also called as an output device because the data comes out of the computer. Next one is speakers. Speakers are going to generate music. Whenever you play some music or a video, then it is going to emit some music out. Now, a speaker is also considered to be an output device. Then we are having plotters. a radium cutter machine, etc. Many output devices are there. You can Google it. So these are input devices and output devices. An input device is a device that gives input to a particular computer. And after processing the data, if the data is emitted from the CPU onto the device, then it is called as an output device. So these are the basic things. Apart from this, we are having a central processing unit. Central processing unit is going to perform all the tasks. A CPU will be there inside your laptop or especially a specific device in your desktop system. Central processing unit. What exactly it has? It has a control unit. Control unit is going to control all the components available in your CPU. A control unit controls all the components in a CPU. That may be input devices, that may be output devices, that may be arithmetic and logical unit, it may be registers, it may be memory. Altogether, a control unit controls. Next, coming to the arithmetic and logical unit. Control unit emits control signals. Control unit emits control signals and it uses control lines. We are going to study that. So what we said, data as well as control signals are shared in the common memory in von Neumann architecture. So coming to next one, that is arithmetic as well as logical unit. In arithmetic unit, we are having arithmetic operations to be performed. What exactly arithmetic operation is? An arithmetic operation means it may be performing addition, it is performing subtraction, division, multiplication, etc. Just a second. Cells. I'm going to share, new share, cell. Share, notepad. Let's go with notepad. Share the screen. Excel, share. Now, I hope you can see the Excel file. Can you see the Excel file? Somebody respond.
Yes, sir.
Yes, thank you. Yeah. So arithmetic operations. What are the arithmetic operations we are having? One is addition, subtraction, multiplication, division, as well as modulus operation. These are the different arithmetic operations that are performed. And so what exactly addition does? It adds. Now, subtraction, I hope everyone knows all these operations. Modulus means a reminder. Whenever you divide something, you will be getting quotient. Quotient as well as a reminder. Now, in computers, whatever the operation you perform, that operation is performed by only addition. That operation is performed only by addition. For example, in arithmetic operations, let us say we are having 1 plus, let us see 0 plus 0. What is the result? You can unmute yourself.
0. 0.
What is 0 plus 0? Basic mathematics. Nothing.
0.
0.
0, sir.
0 plus 0 is 0. Very good. Right answer. So this may be a decimal number. This may be a binary number. Next one is 0 plus 1. The result will be
1.
Is that right? Yeah, 1 second.
1.
0 plus 0 is 0. Then we are going to get the arithmetic operation as 0 plus 1. We are going to get the result as 1. Very good so far. We got one more arithmetic operation, that is addition of 1 and 0. The result is 1. The last one is we are going to add two ones.
1 0.
1 0.
ones. What is the result?
1 0.
0.
0.
0.
This is basic mathematics. Now coming to computers, computer only knows two things, that is 0 and 1. And 1. These are called as binary numbers.
Binary language.
Computer knows only zeros and ones, that is binary numbers. You don't know what exactly 2 means. So you have to write 1 plus 1 as 1 0. This is the binary equivalent of 2. Binary equivalent of 2. How we got it? We are going to study now. Don't worry. Just for your these things. So one more addition part is there, that is 1 plus 1 plus 1 means we are having 1
1
for
1
thrice.
1
Then this is equal to 3 in decimal number system. But coming to
1, 1.
binary number system, you are going to write it as 1 1. So these are the basic things with respect to addition which you need to recollect. Okay, computer don't know what exactly 2 is. Computer knows only zeros and ones. So you can take a notebook or you can keep a paper, whatever is feasible to you, note it down. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1, and 1 plus 1 plus 1 is 11. Not 11, it is 1 1. You should not say 10 here, it is 1 0. Here it is 1 1, binary addition. So what exactly the binary equivalent and decimal equivalent? So decimal, and we are having one more, that is the next one is binary numbers. I'm going to write the decimal equivalent as well as binary equivalent for your understanding purpose. So one is decimal, another one is, one second. Can you see the Excel file?
Yes, sir.
Yes.
Yes, sir.
Very good, nothing to worry. Decimal equivalent 1. So binary equivalent is, let us take 4-digit number. You may have 4-digit numbers, 8-digit number, 16, 32, 64, 128, depending on the bit of the CPU. The bits, 16-bit computer, 32-bit computer, 64-bit computer, like that we are going to call. Let us take the example of a 4-bit computer. Okay, nowadays this computer doesn't exist, but we are going to take it as an example. 4 digits will be there in that particular number. So 0, 0, 0, 0, 1, you are going to get 1. Then for 2, the binary equivalent is 0, 1.
0 1 0.
Very good. Coming to 3,
0 0 1 1.
0, 0, 1, 1. Very good. Good guesswork. 4.
0 1 0 0.
0 0.
Yeah, 1 second. So the screen is visible to you?
Yes, sir.
Yes, sir.
Yes, sir.
0, 0, 0, 1, 0, 0. Can you see one is moving? 0, 1, 0, 0. What happened? 0, 1, 0, 0. Then coming to 5, what happens with 5?
0 1 0
4
1.
plus
0,
1
1.
is 5. 4 plus 1 is 5. So this one, then we got 6. So
0 1 1 0.
0, 1, 1, 0. Very good. Right answer.
0 triple 1.
0 1 1 1.
For 7, we are going to get 0,
triple 1.
1. For 8, we are going to
1
get
triple 0.
1, 0, 0, and goes on. This sequence goes on. So these are decimal values as well as binary values. How you are going to add? Now take the example of 2. What is 2? So the example 2 is 0, 1, 0 is equal to 2. And coming to the binary number 1, 0, 1. So this is binary. Now let us add. What exactly you are going to get?
1 1
What is the result now?
1 1.
1. 1, right? What exactly you are doing here? Just a second. So, Now, what exactly you are going to do? You are going to add these two numbers, 0 as well as 1. So, what is 0 plus 1?
1.
1. And the leftover is 1. So, directly to write 1 as the result. See, 0 plus 1, actually we have seen now that 0 plus 1 is 1. If you see this truth table, not truth table, 0 plus 1 is 1. So what you are writing here, 0 plus 1 is
1.
1. From the right hand side we are coming. Good. So 0 plus 1, you are going to write the result as 1. Then the leftover 1, you are going to carry it as it is. So we are going to get the result as 1, 1. Okay. What is this 1, 1? Just go and cross check. 0, 0, 1, 1. Here we are having 0, 0. So what is the equivalent? 3. So what is the decimal equivalent of 1, 0? It is 2. 2 plus 1, we are getting the result as 3. So our working is fine. Okay, our working is fine. Now, let us do the addition of these two numbers. Let us say 7 plus 5. 7 plus 5. What is the result?
0 triple 1.
What is the result? Nobody knows what is 7 plus 5?
12. 1100.
1100.
7 plus 5. I'm asking about decimal number system. You are concentrating on binary number system.
12.
12.
What is the equivalent? 7 plus 5. Decimal numbers.
12.
12.
12. Very good. Right answer. Congrats. Nobody is answering today. So the answer is 12. See, whenever I write 7, it may be an octal number, it may be a decimal number. It is not binary number. So what is the 7's equivalent binary number? 0, 111.
111.
Is that right? 0, 111 is the binary equivalent of
7.
value 7. What about 5?
0, 1,
0, 1, 0, 1.
0, 1. Is that right? So here you need to do the addition part. So what is this 1 plus 1?
1, 0.
1, 0.
1 and a 0. So what you need to do, write down the 0 here and make this 1 as a carry bit. You need to make 1 as a carry bit. So you are going to write here first of all 0. Then you are going to go, we got 1 bit as carry bit. Yes, 1 bit as carry bit. Now you have to add this carry bit and 1. What is the result?
1, 0.
1 0.
So you are going to add 0 plus 1. So again you got 1 plus 1, that is 1 0. Write down the 0 over here, 1 bit as a carry bit to the next one. Okay. So again you are going to write here 0 and 1 bit what you got is write the carry bit. Okay. Now what exactly you need to do? You need to add 3 digits. 1 plus 1
1 1 1
1,
1.
1.
1 plus 1 plus 1. So what is 1 plus 1 plus 1?
1
1, 1.
So let us divide this 1 plus 1 plus 1. We got 1 and a plus symbol, then 1. So what we got? 1 0. Now, to this 1 0 again add one more 1. Again add one more 1 because we need to add 1 plus 1 plus 1. First we have 1 plus 1, we got the result as 1 0. Now add 1 to it. So we are getting 1 1 as the result. Is that clear?
Yes, sir.
These are the intermediate results. Okay. Now what exactly you have to do? You have to copy this 1 over here. Okay. Already we must have written here 0 in the previous edition. Oh. So we got 0 0. Now what we need to do? We need to copy this 1 over here and we have to move this 1 as a carry bit. As a carry bit. So let us add a carry bit. Now here we need to perform the addition, that is 0 plus, no, we need to copy here 1, right? So from where we got this one? We got the one from here. Here we got this one, and this one is made a carry bit over here. Is that clear? Now we are left over with these last 3 digits, that is 0 plus 0 plus 1. 0 plus 0 plus 1. So what is the result? The result is 1. So finally we are going to get the result as double
1100.
0.
1100.
The result is 11 and 00. Now what is this 1100? Did we got 1100 here? No. Let us keep on writing this one. 8 we got 1 3 zeros. Is that right? What is this 1100? 1100 must be equal to 12. Let us check. After 8, let us write this binary
1001.
10, 11, and we are expecting that our answer is equal to 12. So 9 means add 1 to the above number. 1. Add 1 to the above number. So what it becomes? Then add
1011.
1 to the above number. So 0 becomes 1. Then add 1 to
1100.
1100.
very good. So we are going to get 1100. So 1100 is equal to 12. 1100 is equal to 12. So what is the result we got? The result we got here is, the result what we got here is 1100. The same result, 1100 is equal to 12. So if you do the decimal addition 7 plus 5, we are getting the result as 12. We are converting this 7 into binary numbers. This is what we got. And we have converted 5 into binary number we got. These are the carry bits, and this is the result what we got. Any doubts here?
No, sir.
No, sir.
Anyone is having a doubt? Shall I repeat it again? Otherwise, we are going to move forward.
Move
Binary.
forward, sir.
If you are having a doubt, you can type in chat window.
No, sir.
If there is a doubt, you can type in chat window. Very good. We repeat it, sir. Very good. No issue. So let us again come back. We are having the basic things, that is in binary addition 0 plus 0 is 0. In binary addition 0 plus 0 is 0. Then 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1 0. 1 plus 1 is 1 0. Then 1 plus 1 plus 1 is 1 1. Why? Because we are adding 1 to this particular 0 part. Okay, we are getting 1 and 1. So these are basic additions that are to be performed on binary numbers. Don't write 1 plus 1 as 2. In binary numbers, you are having only zeros and ones. We are doing binary addition now. Inside the CPU, it performs only addition on binary numbers. Whatever the decimal number you get, whatever the octal number you get, whatever the hexadecimal number you get, it is going to convert to binary. Then it performs implementation of that binary process in a CPU. So these are the things that you need to recollect. 1 plus 1 plus 1 is 1, which is almost equal to 3. 1 is equal to 3. So even if you consider these as decimal numbers, 1 plus 1 plus 1, 3, but instead of writing 3, you are going to write the binary equivalent of 3. Okay. Next, what we are doing, simply we are making a chart. What is the decimal number? What is the binary number? So for 0, if we concentrate here, 0, we are going to write all zeros. Then for 1, we are writing 0, 0, 0, 1. Add 1 to this. 1 plus 1, we said 1, 0. Then 2 becomes 1, 0. Then add 1 to it. 0 becomes 1. So 3 means 0 plus 0. That is 0 plus 1. You are going to get 1, 1. Then add 1 to it. See, 1 will be carry. 1 will be carry. 4 becomes 1, 0, 0. Then 5 is 1, 0, 1. 6 is 1, 1, 0. 7, 1, 1, 1. So on you can write like this. Okay, up to any number, it's up to you. I'm going to explain in the next slide how you are going to do this. Then what we are saying, let us take to decimal numbers and do addition part. For example, here we are having 10 plus 1, 11. Very good. It is decimal addition as well as binary addition. 10 plus 1 is 11, but 10 plus 1 is 1, 1. 10 plus 1 is 1, 1. It depends on the base value. It depends on the base value. If the base value is 2, it is a binary number. If the base value is 10, it is a decimal number. If the base value is 8, it is a octal number. If base value is 16, then it is a hexadecimal number system. Now, whatever may be the case, in this case, we are getting both as correct. If decimal you are considering, 11 is the right answer. If binary you are considering, 1, 1 is the right answer. So 2 plus 1 is 3. So 2's equivalent is 1, 0. And 1's equivalent is 1. So you are getting 1, 1 as the result. 1, 1 as the result. Now let us take one more example. What is the example we have taken? Here we have taken the example for this case. Take 7 as well as 5. 7 and 5. The addition always starts from right to left. Addition always starts from right to left. So what exactly you are doing here? Here, first you have to take the rightmost numbers. 1 plus 1. 7's binary equivalent is 0, 1, 1. And 5's binary equivalent is 0, 1, 0, 1. So what you are doing here, you are taking the rightmost two digits, that is 1 and 1. Then what you are doing, you are calculating. What is that? 1 plus 1. What is the result of 1 plus 1? You are going to get 1 and a 0. Take this 0 over here, copy this one, and take this one as a carry bit. I hope you studied this carry bit, etc. in your second or third class. Then after this, what you are going to do, you got a carry bit as 1, then 1, 0. What you have to do next, you have to add the next digits. That is 0 plus 1 plus 1. So what you are going to do? You are going to add 1 plus 1 plus 0. It means nothing but 1 plus 1. What is 1 plus 1? 1, 0. Copy this 0 over here and copy this one as a carry bit. Copy this one as a carry bit. So we got finally 0, 0 and carry bits as 0, 1, 1. 3 bits we got. Okay. Now, next thing what you have to do is you have to add these 3 ones. 1 plus 1 plus 1. 1 plus 1 plus 1. What exactly is this one? 1 plus 1 plus 1. 1 plus 1 plus 1 is 1, 1. Seen what is 1 plus 1 plus 1? The result is 1, 1. Write this one over here and write this one as a carry bit. So here 1 is carry bit. Then what you need to do? Then you need to add the last 3. 0 plus 0 plus 1. So what is 1 plus 0 plus 0? Anything plus 0 is 1. So here you are getting 1. Just copy this one and write over here. Okay, the next bit. Here. So we are going to get the result as 1100. Now try to find out what is that 1100. Now in this case, what we got 1100, just we have written that binary and decimal numbers. So 1100 we got for 12. We got for 12. So our answer is meeting our binary addition 1100, 1100. Though you add 7 plus 5, you are getting 12 and the binary equivalent of 12 is 1100. So this is addition part of ALU. Is this applicable to do two-digit also? Yes, n digits. Okay, you can take n digits, you can try at home. Take a paper, take the pen, try this. Okay, these things you are not going to do in computer. Whatever we are going to study today in today's class, we are not going to do this in computer. In the next lab, whatever comes, you are going to do in your laptop or a desktop system. So this is addition part. Is this clear? Still anybody is having a doubt? You can type it or you can unmute yourself and ask the question. If you are having a doubt, otherwise we are going to go with subtraction part. Are we good to go with subtraction part?
Yes, sir.
Yeah, as nobody's giving anything in the chat and nobody speaking out, let us go with subtraction. So what exactly is subtraction? Subtraction, multiplication, division, whatever may it be the part, again you are going to do addition only. A CPU performs only addition. Subtraction also is converted into addition. Division is also converted into addition. Multiplication is also considered into addition. For example, if you are writing 2 into 3, what do you mean by 2 into 3? Adding 2 thrice. That is 2 plus 2 plus 2. So you are performing addition for multiplication. Is that right? Similarly for division, 2 by 3 means 2 minus 2 minus 2. Okay? You can work it out. Now, just let us concentrate on what is 5 minus 2. What is 5 minus 2? The minus operation is going to give you 3 as the result. 5 minus 2 is 3. Let us take a fresh page. So instead of writing plus here, let us do subtraction. Let us do subtraction. Now what is 7 minus 5? You may say the answer is 2. Great. Now what is 7's binary equivalent? 7's binary equivalent. Let us copy this code again. So let us remove this stuff. Great. Now, so what we need to do? No carry bits, not required. So this is binary equivalent of 7. So this particular part is binary equivalent of 7 and this particular part is binary equivalent of 5. Okay. So what we need to do? Take the least number. Take the least number. So in this case, the least number is 5. So take this particular number and make it 2's complement. What do you mean by 2's complement? 2's complement means 1's complement plus 1 is called as 2's complement. 1's complement plus 1 is 2's complement. Now let us see what exactly we are saying. So take this number and write 1's complement of this number. So 1's complement of this number. What is 1's complement of this number? Converting
1010.
0 to 1 is 1's complement. So what is that? That is equal to 1's complement is 0 becomes 1, 1 becomes 0. So here we got 0, 1, 0, 1. So 1's complement is 1, 0, 1.
Negation.
So 1's complement is 1, 0, 1, 0. Am I clear here?
Yes, sir.
Yes, sir.
So this part is 1's complement. So this part is 1's complement. Now add 1 to this number. So what you are writing here? Plus 0, 0, 0, 1. Add these numbers. Which two numbers? These two numbers you have to add.
1011.
So what is this? 1's complement plus 1 is 2's complement. 1's complement plus 1 is 2's complement. So what is the result that you are going to get now?
1011.
1 plus 0,
1.
1. Very good. 0 plus 1, 1. 0 plus 0, 1. 1, 0, 1. Wow. Straight away we are getting the result. Nothing to worry. So what is that? 1, 1, 1, 1. Is that right? 4 ones we got. What we have done here? Here we have added 0 plus 1. We got the result as 1.
Sir, 1011.
0 plus 1. We got the result as 1. Then we performed 0 plus 0, right?
1011.
Why we
Sir.
got
Sir,
1
1,
here?
0,
Nobody
101.
answered that the answer is 0 here.
1011, sir.
Wow. Then what we got, what we left over 0 and 1. So we got the result as 1. So what is our result?
1011.
Our result over here is not 1111. The result is 1011. Further doubts are there? I can't hear you. A bit louder, please. Sir, as I did. Somebody asked me, sir, I didn't got the link to the VIP batch group. I missed the class till now. Can I get the recording session later? Yes. By today evening, I'll be posting the recording session on YouTube and I'll be sharing the link in our WhatsApp. Nothing to worry. Okay? But don't make it as a habit to watch the videos all the time. Be present in the class and ask the doubts whenever you get it. So let us get back. So what we have done, we have taken a number. The number is equal to 2. Yeah, please mute yourself when you are not answering. Still I'm getting somebody's talking there. Yes. Okay. Now we got 2 as the minimum number. First of all, what we have done, we have taken 2 numbers to subtract. That is 7 and 5. Let us come back again. 7 and 5. 7's binary equivalent is 0, 111, and 5's binary equivalent is 0, 1, 0, 1. So what we have done, we have found which one is the minimum number. Which one is the minimum number? So from 7 and 5, we got 5 to be the minimum number. So what we have done, we have taken the binary equivalent of 5. Then, so this particular binary equivalent of 2 is not 2, this is 5, right?
Yes, sir.
5. Then what we have done, we have made 1's complement. What do you mean by 1's complement? Wherever 1 is there, make it 0. Wherever 0 is there, make it 1. So 0 became 1 here. Then 1 became 0 here. Then 0 became 1 and 1 became 0. So finally we got 1's complement. So this particular part is 1's complement. Then what we are doing, 1's complement plus 1 is 2's complement. 1's complement plus 1 is 2's complement. So add 1's complement plus 1. So finally we got the result as 1011 after performing the addition. On which two numbers we have performed the addition? On 0101 plus 001, we got the result as 1011. So this is what we got as the addition part. So what we have to do, take this number, instead of 5, replace the 5 with this particular value. What we need to do, replace this particular value with 5's value. So we are replacing now. Is that clear? What we have done, we have simply copied. What we copied the 2's complement in the place of the number, what we have taken as input. Now do the addition part on these two numbers, 0111 plus 1011. What is 1011? 2's complement of 5. What is 50101? Is 2's complement is 1011. So now do the addition part. What is 1 plus 1? So what is 1 plus 1?
1 0. 1 0.
Is 1 0. Write the 0 here and write the 1 as a carry bit. So what you are going to get, the result you are going to get here is, the result what you are going to get here is 0, and the rest digits we don't have as of now. So the first bit is 0. And what is the carry bit? The carry bit is 1. Here we got 1 as a carry bit. Now what you have to add which numbers, the next digit, that is 10's place. Take 1 plus 1 plus 1. So what is 1 plus 1 plus
1 1.
Very good. 1 1 is the result. Here you need to write 1 and 1 as a carry bit. So let us change the carry bit to 1 more 1, and here we need to write 1 digit as 1. 10's place we got 1. Very good. Now what exactly we have to do? Now let us move to the hundreds place. In the 100 place, add. What is 1 plus 1?
1 0. 1 0. 1 0.
1 0. So 0 you have to write over the result, and you have to make 1 as the, so here you are going to make 1 as the carry bit. Is that right? Till this part, any doubts? I don't think so. are going smoothly, slowly. Now what exactly we have to do? Now we have to add thousands part. In thousand part, we are having 1 plus carry 1. So what is that 1 plus carry 1?
1
1 0,
One
right?
zero.
0
1 plus carry 1 is 1
1 0.
0.
1 0
1 0. Nothing to carry, you are going to write 1 0. So what we got, the result as 10010. One very important thing, what you have to do is, you have to find how many bits are there in the number. You
4.
have to find how many bits are there. Now,
4.
7, you are having 4. But you are having only 3 ones. Is that right? So 7 is, we can consider 3 ones to be a 3-digit number. We can consider 7 to be a 3-digit number because the 4th digit is 0. In our place we are having 0. So ignore that 0, we are having 3 numbers. But coming to 5, we are having 4-digit number because 1 is there in the 4th place. So we are going to call it as a 4-digit number, 1011, because whatever the 1 is there at the max is called as that digit number. So 1 is available at the 4th location, 4th bit. So we are going to call it as the 4th location. So which one is maximum? 4th bit. Whenever you get any result, take only 4 bits. Ignore the leftmost bit. Take only the rightmost numbers. So we are going to call this as a 4-bit addition. 4 addition. So what you need to do, just copy or take only the first 4 digits. What is this first 4 digits? 0101. And what about this extra one? This extra one is called as the positive or negative identification. If you get 1, it means positive number. If you get 0, negative number. So what we need to do? You need to remove this one. Whenever you perform subtraction, this part you have to do. Okay, this part you have to concentrate. Now what is 0010? What is decimal equivalent of 0010?
2.
2
2,
2
right?
2
00 equivalent is 2. So answer is 2. 7 minus 5, answer is 2. So this is 2's binary number. So let us again revise this. What you have done, you have taken whichever is the minimum number. In this case, 5 is the minimum number. You have taken the 5, do 1's complement to it. 1's complement in 0 becomes 1, 1 becomes in 0, that is inverse. Then 2's complement means plus 1. Add 1 to this, you got that number. Just replace this number with 5. Copy this number, write it at the 5th location. Now add these two numbers. Whatever the result you got, see how many digits are there. 4-digit numbers are there. Take only the rightmost 4 digits. Leave the 5th bit. If the 5th bit is 1, it means it is a positive number. If the 5th bit is 0, it means it is a negative number. Just ignore the leftmost bit. Take only the rightmost 4 bits. So we got the rightmost 4 bits to be 2. I hope it is clear. Any doubts here?
No, sir.
No, sir.
No doubt. Very good.
No.
If anyone is having a doubt, you can unmute yourself or you can type in the chat box. Oh, that's great. Now, similarly, multiplication is performed and division is performed. Sir, explain 2's complement. Very good. 2's complement means what? Just let me correct this 5. So what is 5's binary number? 5's binary is 4 plus 1. So this is 5's binary number. So 5's binary number 7. Now in these two numbers, 5 is the minimum number. In 7 and 5, 5 is the minimum number. Take the minimum number. Suppose, sir, I want to perform 7 minus 7. Take any number. If both the numbers are same, take any number. Now 5 is there. Take the binary number of the minimum value and do 1's complement to it. 1's complement means inverse. Inverse means what? 0 becomes 1, 1 becomes 0. So 1's complement is the inverse of the given number, that is 5. It becomes 1010. Then what you have to do? You have to add 1 to it in order to make it as 2's complement. 2's complement formula is 1's complement plus 1 is the 2's complements formula. So what you are doing here, you are going to add 1 to it, then do the addition part. So these are performed addition. 0 plus 1, you got 1. 1 plus 0, you got 1. 0 plus 0, you got 0. 1 plus 0, you got 1. So finally 2's complement of 5 is 1011. Now copy this 1011 and replace the value of 5 with 2's complement of 5. 2's complement of 5. Then do the addition part. Now what is the addition part? You need to add 1 plus 1. You need to add 1 plus 1. Then add 1 plus 1 plus 1. What is 1 plus 1? 1 and a 0, right? Now move this 0 bit over here. Then move this 1 as a carry bit. So I am writing here carry bit as 1 0. Initially we have carry bit as 0. Then what we need to do? Add 3 ones. Yes, add 3 ones. What is the result? Adding 3 ones?
1
1 1. Very good. So copy this single digit 1 to the answer and the next 1 digit as a carry bit. Okay. So here we are going to get 1 0 as answer, and here you are going to get one more carry bit. Okay. Then again you are performing addition on this 100 digit. So we got 1 plus carry 1. 1 plus 1, we got the result as 1 0. Now write the 0 in the result and 1 is the carry bit. 1 must be the carry bit, 0 must be added to the result. So here we are going to add a 0 bit and we are going to add a carry bit as 1. Now what we need to do, we need 1 plus 0 plus 1, thousands place. Add 1 plus 0 plus 1, what we got? Plus 0 plus 1 is again 1 0. Now we don't have any other number, so directly write that answer in the result 1 0. So what is the number we got? 1 0 0 1 0. Okay, totally we got 5 digits. Now if you concentrate here, maximum wherever that is the number of bits we are going to consider. In this one, the leftmost one is at the 3rd digit, so we are going to call it as a 3-digit number. Now here if you see, we are having 1 at the 4th digit, at the 4th digit, so we are going to call this as a 4th digit number. So what we are going to do, whichever is maximum, we are going to consider those many number of digits. So maximum, 4 is the maximum. So from the right hand side take 4 bits. From the right hand side take the 4 bits. So 0 1 0 0. Okay, we are going to consider 4-digit number only whenever you are performing subtraction, 2's complement, then only take this. In addition part, don't consider this formula. Okay, the number you get, take it as it is. But when you perform 2's complement, you need to take the number of digits. What are the number of digits as input you have considered? Now take only those 4 digits. What about the leftover 1? Now 1 represents a positive number and 0 represents a negative number. You can even perform this operation on negative numbers. Okay, so we have taken that particular number, 4-digit number. So what we got is 0010. So what is 0010? It is the equivalent of 2. Even if you consider 7 minus 5 in decimal number, the result is 2. Hence our addition is correct with respect to subtraction. Hence our addition is correct with respect to performing 7 minus 5. Okay, any doubts here further?
No, sir.
Great. So these are arithmetic operations that are performed. Addition means you are adding. Subtraction means you are performing 2's complement and adding. Multiplication means adding that number for those many number of times. Division means subtracting that number for those many number of times is called as division. So altogether, computer knows only addition, which is again converted into subtraction, multiplication, division, etc. Okay, so this is arithmetic part of ALU. So the leftover is, one second. Yeah, we are having this new share. So we have completed arithmetic part. The leftover is logical part. In logical part, we are having logical operations to be performed on bits. Binary number bits, 0 or 1. So what exactly is logical operation? In logical operation, we are having 3 things. One is and. And operation, this is the symbol represented for and operation. Don't worry now itself. Okay, that you are going to study in your electronic subjects, which are going to be dealt in your next semester. Now, just concentrate on these numbers, or these are also called as truth table. Now, 0 and 0, the result is 0. 0 and 1, the result is 1. 1 and 0, the result is 0. 1 and 1, the result is 1. Okay, only when both the inputs are 1, the result is 1. If you convert these numbers to the truth tables, true and true is only true. The rest of the cases it is false. False and false, false, false and true, false, true and false, false, and true is only true. Now let us come to the next logical operation, that is OR. Now this is the symbol for OR, and coming to the R truth table, or truth table, 0 or 0 is only 0 and the rest are true. Rest are ones. 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Okay, only 0 or 0 is 0. Now you need to concentrate here. Don't write 1 or 1 as 1 0 or 1 and 1 as 1 0. These are different. Arithmetic operations are different. Logical operations are different. So what we say, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. In other words, false or false is false, false or true is true, true or false is true, and true or true is true. So this represents OR truth table. Now coming to the leftover, that is not. Not means negation. 0 becomes 1, 1 becomes 0. So these are the three logical operations that we are having, and, OR, and not. Somebody asked while subtracting, why we have to take only 2's complement, sir? That is the process. That is the process. Whenever you are subtracting, the computer does that. We are also going to do the same thing. Okay. So coming to logical operations, we are having OR, and not, which are performed on binary numbers. Now let us see, apart from logical operators, what a CPU has. CPU has registers. CPU has registers. What registers it has? It is having a MAR, memory address register. It has memory address register. What it has? It holds the memory location of data that needs to be accessed. That needs to be accessed means the address of a variable. For example, if you are writing C is equal to A plus B, for that you need to know what exactly is A is, what exactly B is, what exactly are the addresses of those two variables. Let us see that example. Let us complete first of all the registers, then we are going to see one after another. MDR, memory data register. What it has? It holds the data that is being transferred to or from the memory. It has the data. MAR has the address. MDR has the data. Accumulator. Accumulator is used to store intermediate results. Intermediate results means whenever you calculate a particular equation, an expression is evaluated, it may generate some intermediate results. Those intermediate results will be stored in accumulator. Let us see, don't worry. Program counter, PC. Program counter is going to hold the next instruction to be executed. After executing this particular instruction, what is the next instruction to be executed will be stored in accumulator. No, in program counter. So what we mean here is a program counter holds the address of next instruction to be executed. Next one is CIR, current instruction register. Current instruction register in the sense the instruction which is under execution, its address will be stored. Current instruction register will have the address of the instruction that is being executed. Now let us see one example with all these registers. New share. Wow. Now let us take registers here. that is MAR and MDR, then accumulator, then we are having program counter, and one more is there, CIR, current instruction register. Okay, what exactly they have values, let us see one by one. Initially they may have a 0 value, a blank, maybe a garbage, we don't know. Okay, maybe a garbage value, maybe a 0 value, or maybe the previous instructions value, we don't know exactly. What we need to do, we want to execute C is equal to A plus B. In mathematics you might have written x plus y is equal to 0, something like this. Okay, you might have written the expressions ax square plus bx plus c is equal to 0. The right hand side you will be getting the result. In computers you will be getting the result at the left hand side. So what you are going to write, you are going to write something like this. If you want to evaluate a plus b and want to store in c, you are going to write c is equal to a plus b. You are going to evaluate like this. C is equal to A plus B. You are not going to evaluate the instruction from right to left. You are going to execute, no, left to right. Here you are going to execute the instruction from right to left. Okay. So what you need to do, take the B value, take the A value, add them and store them. In order to do this, we need to know what exactly is B value. Let us say B value is equal to 20. Then we are saying A value is equal to 10. What we need to do, we need to perform C is equal to A plus B. That is our intention to do. In order to do this, A must have some memory. So let us say this particular box as A. And the value inside A is 10. Let us say it is having some address, some garbage address. Okay, let us say the address is 100. Okay, similarly, we are having one more memory location called as B. Similarly, we are having one more memory location called as B. What B is having? Value 20. Okay, and let us say the address is 200. We have one more memory location called as C, which must store the result. Let us say the register name is C. It has initially, and the address is, for example, let us say 3. Okay, so this is what is going to happen. We will be having memory locations for all the variables. We will be having memory locations for all the variables. Means A, B, C are called as variables. As of now, they are also called as identifiers. Don't worry, when the time comes, we are going to study. Okay, so every instruction will have some address. Let us say 500, 501, 502. Okay, let us say every instruction has a address in computer. Every instruction, whatever you write, will have address. Okay, now let us say one more instruction is there after this 503. Okay, what exactly it is? May have some more lines bottom to these lines, and maybe above this line also we may have some instructions. Okay, now let us concentrate on these lines. Now instruction execution starts one instruction at a time. So what is the instruction to be executed? A is equal to 110. So A will be having 10. What MAR has? Memory address register. Memory address register
100.
means the register A will have some value, that is 10, and that 10 will have an address. Write that address in MAR. Is that clear? I'm going to move this C from here in order to avoid part issues. Okay. MDR is having 100. What MDR will have? MDR will have whatever the value is there in A. A is having 10. Memory data register. What is the data? Value 10.
10.
What you want to do? Store 10 in A. That is what we need to do. Accumulator will have intermediate result. What is the result? 10.
10.
10 will be stored in accumulator. Program counter next. After executing this,
501.
501 address is the next instruction. Very good. So program counter will have 501. Very good. Next we are having current instruction register, which is
500.
execution.
500.
Instruction is under execution. So we are going to write here 100. So this is what is going to happen inside a computer processor. MAR has 100, CIR has 10, accumulator has 10, program counter has 501, CIR is having 500. Now let us execute the instruction. B is equal to 20. What is the address of B? 200. Now we have 200 in MAR. What is the data in it?
20.
20.
20. So write down 20 over here. Next instruction we are executing. What exactly accumulator has?
20.
20.
20.
10.
20. Instead of 10, we are having 20. What program counter has?
502.
What is the next instruction address?
502.
502, which has to be executed after performing this operation. Current instruction?
501.
Not 1.
501. Very good. So you can see registers now inside a CPU. So this instruction is also executed. Now we are going to write C is equal to A plus B. So what is B? Then what is A? Add them, store them. So we are performing operations here. What is B? From right to left you need to move. What is B? What is A? What is C? So first you are going to have MAR. What is B? What is the address of B? 200. So MAR has 200 now. What the value it has? Same value 20. We are dividing and executing this instruction. C is equal to A plus B. What you are going to take? Take the B value, add to A value, store it in C. 3 operations we are going to perform, 3 instructions. So first instruction is take the B value. For that you are writing the code here. That is memory locations. So what accumulator will have? 20. What program counter has? Program counter has next instruction address 503. What is under execution?
502.
2. Very good. So 502 is under execution. You are going to write 502 in CIR. 503 is the next instruction. You are going to write 503 in program counter. Then 20, 20, 200. So what we have done, we have taken B value. Some book says that in program counter, again you are writing 502. Some book says so. It's up to you because we are going to execute the next part in the same instruction. So program counter may also have 502 again because we are residing on the same. We are going to take A value. Okay. Now, what is the address of A?
100.
Now MAR has 100 in it. We are taking the value of A now. What is MDR? MDR
10.
has 10.
10.
So what you are doing? A plus B. So what you are having already, accumulator has 20. 20 plus 10 you need to do and store that in accumulator. So here you are going
30.
to get the result as 30. Accumulator has 20 plus 10. See, the instruction is A plus B. So you are taking 20 plus 10. These two you are going to add 20 and you are going to take 10 and you are going to do whatever the result you are going to store in accumulator. So after this, the program counter is still there in 502. Some book says 503, some book says 502. It's up to you. Both are correct. And current instruction register is also 502. After adding C A plus B, what you need to do? You need to store in C. What is the address of C? 300.
300.
Okay. Now what MAR has? 300. MAR has the result
30.
30. What accumulator has as it is
30.
30. Accumulator also has as it is 30. What about program counter? Next is
502.
not 3 here. Not
503.
502. Then here what we are having current instruction register
502.
502. Very good. So these many instructions are executed for this single C is equal to A plus B. We need to know what is A equal to 10. We need to know what is B equal to 10. Then we need to get C is equal to A plus B. So this is A equal to 10. What about this expression? B is equal to 20. Now these instructions are C is equal to A plus B. Same thing, C is equal to A plus B, C is equal to A plus B. So this is how our CPU is going to do the task. MAR, address register, MDR, data register, accumulator, values, program counter, addresses of the next instruction, CIR, execution of the current instruction. All together, it is going to use same memory in von Neumann architecture. Same memory is used in von Neumann architecture. Any doubts here?
No, sir.
No, sir.
Yeah, please tell everyone to mute their voice when you are not answering. Please mute yourself, others are getting disturbance. Kindly support. Very good. Now let us move to the next slide. Let me share. Now, apart from registers, we are having buses. What do you mean by bus? A bus is a wire that connects multiple devices, memory, etc. A bus is a wire inside a computer. We are not going to call it as a wire. We are going to call it as a bus. What exactly bus, or how many types of buses are there in von Neumann architecture? 3 types. One is address bus, data bus, and control bus. Please mute yourself, everyone. Mute all. Yes. Now coming to address bus. What address bus? By names, it carries address of the data between processor and memory. It carries the address of data between the processor and the memory. Means, in other words, this is connected to MAR, memory address register. Okay, carries the address of data between the processor and memory. And what else it may be carrying? It may be carrying program counter data, the address. Maybe CIR, current instruction register. It also has an address. So all the addresses are moved between the processor and memory using address bus. Next one is data bus. Data bus carries the data between the processor and the memory unit and the input output devices. It carries the data part. Okay. Next one is control bus. In order to control the address bus, data bus, and different components, we are going to use the control bus. Control bus carries control signals or commands. What do you mean by command? Add, sub, mul, div, MOV, move, JMP, jump. Like this, we'll be having different commands. Inside the processor instruction set, we have set of commands. Now, those commands or signals are carried by a control bus from the CPU and status signals from other devices. Status signals in the sense what? You have pressed the power button, it sends a status signal, switch off the computer. Okay, you have pressed the button on your optical disk drive, it has to open the tray, a signal is moved to open the tray. All this comes under control bus, that is status signals from the other devices. In order to control and coordinate all the activities within a computer, all the activities are performed by control bus. The controlling part of address bus, data bus, different components is performed by control bus. So we are having 3 different buses and the rest we have seen so far. Now let us see how many types of memory is there. Generally speaking, we are having 2 types of memory. That is RAM, random access memory. Random access memory is also called as RAM. What it has the program under execution. Whatever the program you are executing, that will be loaded into RAM first. Then only it is moved to the CPU. If you are watching a movie, the movie is moved to RAM. You may be having 8 GB RAM, 4 GB RAM, 16 GB RAM. Now, if the RAM is more, the CPU is going to perform the operation fast. If the RAM is less, the CPU has to move the data continuously. Okay, simultaneously it is going to move the data. So it depends on RAM size also. The speed of the computer depends on RAM size. What is RAM? RAM is a volatile memory. Volatile memory means what? If you shut down the system, if you restart the system, then the data inside RAM is lost. It will not reside in RAM. It is only a temporary location for execution. RAM is a temporary location for execution. You may have RAM in mobile phones also. You may have RAM in mobile phones also. So what it does, it loads the data from the hard disk onto the processor. Okay, intermediate one. RAM is of many types, like SRAM is there, dynamic RAM, static RAM, DDR1, DDR2, DDR3, many are there. Okay, you can go to Google and find different types of RAMs. Okay. Apart from RAM, we are also having a read-only memory called as a ROM. ROM is a permanent memory. We cannot modify. Only things that are modified are a very few. That is, you can rewrite the address of the operating system. Though we are not going to rewrite, the operating system is going to write the starting address of operating system. Now, whenever you set date and time, that date and time is also set in ROM. ROM is a permanent memory which is made by the manufacturer. ROM is created by the manufacturer. Some says it as BIOS ROM. Okay, basic input output system ROM. Whatever may be the case, ROM is a permanent memory where you switch off the computer, the data is not lost. Okay. So mainly two types of memories are there, RAM and ROM. The rest of the types you are going to study in your PTT subject. Now, like currency, we are having the measurement for memory. Coming to currency, we are having the measurements as 10 rupees, 20 rupees, 50, 100, 500, 2000 in the present era. In the same fashion, a computer memory also can be measured in these types. That is, 1 byte is 8 bits. A bit is the tiniest location in a memory, which is going to store either a value 1 or a value 0 in it, is called as a bit. So 8 bits, if you combine, it is called as 1 byte. 1024 bytes is 1 kilobyte. 1024 kilobytes is 1 megabyte. 1024 megabyte is 1 gigabyte, and so on. Okay, all the terminology is listed there. Gigabyte, terabyte, exabyte, zettabyte, petabyte, yottabyte, many are there. You can Google it for further information. Only thing is, we should not say 1 KB is equal to 1000 bytes. It is 1024. In computer terminology, everything is measured in 1024 format. So let us move. Advantages. Somebody typed, sir, I am from EEE branch. I attended this class. No worries. In my class, we are having CSC, EC, EEE all together. Now, coming to the advantages of von Neumann architecture. What are the advantages? Now, if you see, the best example of von Neumann architecture is a ATM machine where you can do only one task, or a small mobile phone which is not a smartphone. If you open messages, you cannot make a call unless you come back to the home screen. If you open messages, you can't make a call. You have to come back to the home screen. Then you can open call. If you want to see the messages again, you need to go back to the home, then open the messages. At a time, it is going to do only one task. That is the best example of von Neumann architecture. Whereas coming to smartphone, you can open more than one application at a time. You can open more than one application at a time. You can open WhatsApp, you can open phone, book, you can open any other document simultaneously. Okay. Now that is based on Harvard architecture, not von Neumann architecture. Almost all the servers are based on Harvard architecture using CISC architecture, RISC architecture. Many are there you are going to study in PTT subject most probably. Now let us see one by one what are the advantages we are having. Control unit retrieves the data. In von Neumann architecture, control unit retrieves the data and instruction in same manner from one memory. Yes, it is not going to distinguish data part and control part. Everything is considered as same. In whatever the manner it receives, it is going to disseminate in the same fashion. Next, design and development of the control unit is simplified, cheaper and faster. Okay. Because we are following von Neumann architecture and a set of instructions are predefined, the cost is also reduced. Design and development of control unit is simplified, cheaper and faster. But we are not going to manufacture any computer. That is done by the manufacturer himself or herself. So the cost is reduced. That is what we need to tell as an advantage. Then we are getting data from input or output devices and from memory are retrieved in the same manner, because for everything the memory is same in von Neumann architecture. Either it may be the data may be received from an input device or from a output device or from the memory. Whatever the data comes is retrieved in same manner. Okay. Next one, organization of memory is done by programmers, which allow them to utilize the memory's whole capacity. Okay, you can utilize the memory's whole capacity. Why? Because registers are given in advance. These are the registers that are available. You can make use of them. But we are having limited number of registers in any CPU. If you see the latest one, 32-bit computer, we will be having extra integer registers from R0 to R31 and floating point registers F0 to F31. If it is a 64-bit computer, we will be having registers from R0 to R63 and F0 to F63 are the floating point registers as well as integer registers. So a programmer like you and me can use these registers to speed up the execution process. Registers are the fastest memory that can be processed by a CPU. Registers are the fastest memory that can be processed by a CPU. That's why we are going to make use of the registers that are available in programming. That is what is an advantage. Somebody asked, sir, class timings. I hope you received your timetable in that you are having class timings. Now coming to disadvantages, somebody asked, can you show the previous slide? I'll be sharing the video with this by to end of the day. Don't worry, you can see there. Because we are running short of time, we can't go back and back. If you are having a doubt, you ask, I'll go back to the previous slide. Now coming to the disadvantages, we are having disadvantages with respect to von Neumann architecture. And these are the advantages of Harvard architecture, in other words. Disadvantages of von Neumann architecture and advantages of Harvard architecture, both are same. So parallel implementation of programming is not allowed due to sequential instruction processing. We cannot execute two instructions simultaneously. We can't open two applications simultaneously in von Neumann architecture. Only one instruction can be executed at a time. That's why we cannot perform parallel processing. Then von Neumann bottleneck instructions can only be carried out one at a time and sequentially, the same thing. This is also called as von Neumann bottleneck. Bottleneck in the sense what? We cannot move our heads, or we cannot do, or we cannot overcome this part. So that's why we are going to call it as von Neumann or bottleneck of any technology. So what it is, instructions can only be carried out one at a time. We cannot execute more than one instruction, and that too in a sequential manner. The above one was parallel implementation, means two instructions executing at the same time. Okay, maybe randomly. Here in this bottleneck is we can execute all the instructions in a sequential manner and at a specific time. What is the risk? The risk of an instruction being rewritten due to an error in the program. Suppose the CPU is requesting for a memory location, the data is there, that if the data is not there, again it rewrites the code to get the data. Again it rewrites the code to get the data. I want the data of a particular register, say A. Now that A value is not received yet. The data has to be loaded from hard disk, secondary storage device onto the RAM. The data is not loaded. Maybe the bad sector is there or the data is not available. In either of the cases, the CPU is going to rewrite that instruction, get the data, get the data, get the data, like that. It is going to repeat till it gets the data. So that is the risk of an instruction being rewritten due to an error in the program. Or maybe you are executing the program for infinite number of times. That is also another issue. You need to restart the system. You cannot come out of the system. So these are some of the disadvantages of von Neumann architecture. Now, what exactly we have learned in this particular session is we have learned von Neumann computer architecture. Apart from that, we have seen arithmetic operations. What arithmetic operations we have seen? Addition and subtraction. We said that multiplication is also addition and division is also subtraction. Altogether, we said computer can do only addition. It cannot do subtraction. It can do only addition. And in order to do subtraction, it has to make the ones complement and twos complement of the minimum number. Yes, in arithmetic operations, we have seen 0 plus 0 as 0, 0 plus 1 as 1, 1 plus 0 as 1, and 1 plus 1 as 1, 0. And if you take 3 ones, the result is double 1. Binary numbers are different, decimal addition is different. Then we have seen at this topic F section completed, but we don't have next class. You are having next class after lunch. Check your timetable. So logical arithmetic operations, we have seen addition. In order to do subtraction, we have addition, then we had 2's complement. How to get 2's complement? 2's complement is 1's complement of a number plus 1. Okay, 1's complement means inversing the number. Inverse the given number, then add 1 to it, you are going to get 2's complement. So that is arithmetic operations. Coming to logical operations, we have seen AND operation, OR operation and NOT operation. If both the values are true or 1, then only the result is true or 1. Otherwise, the result is 0 or false with respect to AND. Coming to OR, if any one of them is true, then the result is true. Otherwise, the result is false. Means for 0 or 0, the result is 0. For the rest of the cases, the result is 1. 1 or 1 is also 1. Then we have seen the NOT operation, logical operation. NOT means inverse. Inverse means what? 1 becomes 0, 0 becomes 1. That is the NOT operation. So these are the logical operators what we have seen. Coming to registers, in registers part, we have seen MAR, MDR, accumulator, program counter, current instruction register. So these are the registers that we have seen with respect to von Neumann architecture. MAR holds the address of a register. MDR holds the data of that particular register. Program counter holds the address of next instruction. Current instruction register holds the address of the current instruction being executed, and accumulator holds the intermediate results that are executed, that are stored, that are acquired under execution of a instruction. Apart from these, we are having registers like integer registers R0 to R31 if it is a 32-bit computer. Sir, next class of F section is number systems. Next class of mine is number systems. Okay. Again, we are going to meet on Friday afternoon. In that session, I am going to take number system. Sir, I do not attend our classes since starting of online classes. Today is the starting class of IP. Okay, don't worry. I am unable to understand anything, sir. Will you please provide me all the recordings since class day 1? I am not responsible for all the recordings. I am responsible only for my class. For the rest of the classes, you can ask the concerned faculty to share the video lectures. I will be sharing the video lectures of my own subject, not others. Okay. By the end of the day or tomorrow, you will be getting the link in the group where you got registration, that is Zoom link. Okay. In the same WhatsApp group, you will be getting the link. Don't worry. So registers, we are having the registers R0 to R31 for integer registers if it is a 32-bit computer. If it is a 64-bit computer, R0 to R63 integer registers will be there. Apart from that, we will be having floating point registers. Floating point, why we are saying explicitly means it will be having exponential part and mantissa part and needs some more storage space to store. So in a 32-bit computer, you will be having F0 to F31, and in a 64-bit computer, F0 to F63. Nowadays, we are having all 32-bit computers or 64-bit computers. What do you mean by bit of a computer? The operating system. Open your computer, right click on it and see the properties. You will be having 64-bit operating system, 32-bit operating system. If it is 8-bit, you will be having F0 to F7, R0 to R7. So that is regarding registers. Apart from registers, we have seen system bus, CPU system bus. A bus is used to connect devices in a computer. We are having 3 types of buses, that is control bus, data bus and system bus. Next one is memory, specifically saying memories of 2 types. One is a RAM, another one is ROM. RAM is a volatile memory. Once the power is lost, the data is lost. ROM is non-volatile memory. Even the power is lost, the data is not lost. It's called as non-volatile memory. Then we are having many types of RAM, many types of ROMs are also there. You can Google it. Core i5 belongs to which bit? No. i5 is the processor. On that, what is the operating system you are installing? That means, is it a 64-bit computer operating system, Windows 10 or any other operating system? If it is a 64-bit, then you can consider 64-bit. Processor bit depends on the manufacturer. You can read the processor help file if you are, it is available on internet. Core i5, how many bits are there, what are the instruction sets, how many registers are there, all these things you can Google it on internet. Okay, sir, for E section they already completed number system last Tuesday. Na sir, no, nothing to worry, you can listen again. More times you listen, more knowledge you gain. Nothing to worry, because if I don't repeat, the rest of the people are going to lose that concept. G, we didn't started even. Okay, don't worry, I am restarting the subject. Today we have seen the first concept, that is von Neumann architecture. If it is repeated, you can learn more. If anything is missed, you can ask as a doubt by the other faculty. Now, apart from this, we have seen memory. Memory will be having different types, bits, bytes, kilobytes, etc. Apart from that, we have studied advantages and disadvantages. Sir, is this class for F section also? Some students are there from E, some from F, some from G. Okay. Not all F section. Now coming to two questions are there. You can answer them using chat window. Don't unmute yourself. Open the chat window and type.
1945.
ADVAC was published in which year? I said don't unmute yourself. Type in chat box. The other should not know the answer. 1945, 1947, 1024, 2020. Yeah, 1945 is the right one. Next one is AC stands for alternate current, accumulator, air conditioning, and Alice C. With respect to today's class, you can type the answer in the window, chat window. Wow, great. Everyone is giving the right answer. Lovely. Love you all, men. I hope you are following my class. So as today is the initial class, I am going to stop the class here itself. From the next week onwards, you will be having the class till 12:30. Okay, the full time we are going to utilize. As this is the first class, we are going to stop here. Any doubts are there, you can ask.
No, sir. Thank you, sir.